In this section, you will learn about the derivative and tangent line problem. First up, a review of tangent lines and secant lines. In your geometry class, you learned that a line that intersects the circle in just one point is called a tangent line, and a line that intersects the circle in 2 points is called a secant line. In calculus, we relate the slope of the tangent line to the instantaneous rate of change of the function. As a point moves along the curve, the slopes of the tangent line at each point become the values of a new function called the derivative. Let's take a look at this diagram. We have a curve here, and at this point, this would be the tangent line. And the slope of that line is the instantaneous rate of change of the function. So in this case, because this is the tangent line, the slope of the tangent line and instantaneous rate of change are negative. In this diagram, at this point on the curve, here's the tangent line. So the slope of the tangent line and instantaneous rate of change are 0. And in this diagram, at this point on the curve, here is the tangent line. So the slope of the tangent line and instantaneous rate of change are positive. Next up, you will discover how the slope of the tangent is the limit of the slopes of the secants. First, a quick algebra review. Given any 2 points on a line, x1, y1, and x2, y2, we know that we can find the slope, which we call m, by doing y2 minus y1 over x2 minus x1. And that would give us the slope of any line. So then that means we can find the slope of the secant lines in this diagram. Let's just start off with this first line right here. And we call this a secant line to the graph because it intersects this curve in 2 points, here and here. And this line is going through the points x plus delta x, comma, f of x plus delta x here, and this point over here, which is x, f of x. So then to find the slope of this secant line, we have to do y2 minus y1. Well, that's going to be f of x plus delta x minus the y value here, which is f of x, over x2 minus x1, which would be x plus delta x minus x. And then we see in the denominator, the x here will cancel with the x here. Nothing in the numerator will cancel. So then we can simplify to say the slope of the secant is going to equal f of x plus delta x minus f of x over delta x. Now what we want to explore in this diagram is what happens to this secant line as delta x goes to 0. So delta x is the distance between these 2 points, because if we take x plus delta x and subtract x, we are left with the difference, which is delta x. And we want to move this point right here, this x value, closer and closer to x, which means delta x has to get very tiny and approach 0. Now on this diagram, if delta x got smaller so that x plus delta x was here, then we would have this secant line. As delta x got smaller so that x plus delta x was here, we would now have this secant line. Let's explore this a little further with an animation. So now let's zoom in on this diagram. Here's the curve, which is in black. We have the tangent line going through the point x, f of x in red. And then we have the secant line in blue, which goes through the point x, f of x, and x plus delta x, comma, f of x plus delta x. Now this program didn't have a delta symbol, so I'm using this for delta x here and here. Now you can see that the slope of this blue secant line is different than the slope of the tangent line. It's actually steeper. Now, if we let delta x get smaller, say to here, the slope of that secant line is still different than the tangent line, but it's a little bit closer to the slope of the tangent line. And if we let delta x get smaller, moves down here, then the slope of the secant line is even closer to the slope of the tangent line. And if delta x gets smaller again, then the slope of that secant line is getting closer to being the slope of the tangent line. And as delta x gets smaller and smaller and smaller, you can see that the slope of the secant line is getting closer and closer to equaling the slope of the tangent line. And as delta x goes to 0, the slope of the secant line becomes exactly the same as the slope of the tangent line. So if we review what we just learned here, we've got a point on the curve at x, f of x, and then we have a second point on the curve at x plus delta x, f of x plus delta x. And as we let delta x go to 0, that second point moves closer and closer, and the slope of the secant approaches being the slope of the tangent line. So as delta x approaches 0, the slope of the secant line approaches the slope of the tangent line. So we can say that the slope of the tangent is equal to the limit as delta x goes to 0 of the slope of the secant line. And remember that the slope of that secant line is given by this difference quotient here. So then the slope of the tangent line is equal to the limit as delta x goes to 0 of the quantity f of x plus delta x minus f of x divided by delta x. This brings us now to definition of derivative. These symbols right here, where we have f and what looks like an apostrophe with the x in parentheses, is read f prime of x. And it stands for the derivative of f. The derivative of f at any x is given by f prime of x is equal to the limit as delta x goes to 0 of the quantity f of x plus delta x minus f of x over delta x. Remember we said that the slopes of the tangent line anywhere along the curve give the values of a new function called the derivative. And this limit is what gave us the slopes of the tangent line. Therefore, the derivative will equal this limit. In this example, find the derivative of f of x equals radical of quantity x minus 3. We know that f prime of x is the derivative, and it is defined to be the limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x. So then for this f of x equals radical x minus 3, f prime of x is going to equal the limit as delta x goes to 0. We have to do f of x plus delta x. So that means our input here is x plus delta x, and that has to go in where the x is. So that's going to be the square root of x plus delta x minus 3. Then we have a subtraction symbol, and then we have to subtract f of x, which we know is the square root of x minus 3. In the denominator, we have delta x. Now, if we tried to plug in and do a direct substitution, this would be 0 because delta x is going to 0. So we would have radical x minus 3 minus radical x minus 3, which is 0, over 0 in the denominator. We know that 0 over 0 is indeterminate, which means we need to do something here. And the technique we want to use is multiplying by 1 in the form of the conjugate of the numerator over itself. So we will do the square root of x plus delta x minus 3 plus the square root of x minus 3, and then the same exact thing in the denominator, square root x plus delta x minus 3 plus square root of x minus 3. Let's bring down the equal sign. Limit as delta x goes to 0, because we have not done this limit yet. Let's get the fraction bar in there. Now, we're going to use a rule from algebra that says a minus b times a plus b is equal to a squared minus b squared. This is our a minus b. This is our a plus b. So then here we will have a squared minus b squared. So squaring this first term, we would get x plus delta x minus 3. And then we have to subtract the square of the second term, which would be x minus 3. Now in the denominator, we just have to multiply straight across. So we have delta x times the quantity square root of x plus delta x minus 3. Then we have this plus sign here, and the radical x minus 3. Let's simplify. We get limit as delta x goes to 0. Let's get the fraction bar in there. In the numerator, we need to clear out these parentheses. On this first term, of course, we can just drop the parentheses, x plus delta x minus 3. For this second term, we will need to distribute the negative sign. So we get minus x and a plus 3. In the denominator, nothing is going to simplify. So we have delta x times the quantity square root of x plus delta x minus 3 plus square root of x minus 3. So continuing to simplify, we bring down the equal sign and the limit as delta x goes to 0. We have to keep writing this limit because we have not performed the limit yet. We get the fraction bar in there. Now in the numerator, the x will cancel with the minus x, and the minus 3 cancels with the plus 3. So the only thing we have left is the delta x in the numerator. Nothing has changed in the denominator, so we still have delta x times the quantity square root of x plus delta x minus 3 plus square root of x minus 3. Bring down the equal sign, limit as delta x goes to 0. Now we see that the delta x in the numerator will cancel with the delta x in the denominator. Get the fraction bar in there, and we have 1 over the square root of x plus delta x minus 3 plus the square root of x minus 3. Now we can do a direct substitution, and remember that it's not x that's going to 0, it's delta x. So the 0 goes in for delta x. Now, in doing that direct substitution, we have performed the limit. So for the first time, we no longer have to write limit as delta x goes to 0. We get the fraction bar in there. The numerator is 1. In the denominator, this first term becomes square root of x minus 3, because remember, the delta x went to 0. Then we have the plus sign, and the second term, square root of x minus 3. These two are like terms, so we can combine them. So this is going to equal 1 over 2 radical x minus 3. So then this is f prime of x, which is the derivative of f of x equals radical x minus 3. Next up, we talk about different notations for derivative. Given y equals f of x, there are several equivalent notations for the derivative. We've already talked about this first one, which is read f prime of x. This notation is read y prime. This one is read the derivative of y with respect to x, or dy dx. And finally, this notation is read the derivative with respect to x of f of x. And you will see that we use all of these notations interchangeably. In this example, given that y equals 5 over x, find the derivative of y with respect to x. Now remember that dy dx is equivalent notation for finding f prime of x, where f of x is equal to 5 over x. So then dy dx is equal to f prime of x, which by definition is the limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x. So this is going to equal the limit as delta x goes to 0. We have to do f of x plus delta x. So that's going to be 5 over x plus delta x then we have to subtract f of x, which is 5 over x, and then that whole thing goes over delta x. Now, if we tried doing a direct substitution at this point, we would end up with 0 over 0. So what we want to do is multiply by 1 in the form of the LCD, the least common denominator, over itself. Our LCD is going to be x times the quantity x plus delta x. Remember, we can only ever multiply by 1. That's why we have to have the same thing over itself. Now this is going to equal limit as delta x goes to 0. We put the fraction bar in there. In the numerator, we have to distribute this x times x plus delta x to each of these two terms. When we take it times this first term, the x plus delta x will cancel with the x plus delta x, and we are left with 5x. Then we bring down this minus sign. When we multiply this second term times x quantity x plus delta x, the x's will cancel, and we are left with 5 times the quantity x plus delta x. In the denominator, nothing cancels, so we have delta x times x times the quantity x plus delta x. Let's continue to simplify. Equals limit as delta x goes to 0. In the numerator, let's bring down this first 5x. Then we will have to distribute this minus 5 to each of these two terms. So we get minus 5x and minus 5 delta x. Nothing changes in the denominator. So we have delta x times x, quantity x plus delta x. Continuing to simplify, we get limit as delta x goes to 0. In the numerator, 5x and minus 5x will cancel, so we are left with this negative 5 delta x. In the denominator, we have delta x times the quantity x plus delta x. This will equal limit as delta x goes to 0. Now the delta x in the numerator and the denominator will cancel. So now we have negative 5 over x times the quantity x plus delta x. Now we can plug in 0 for delta x, and this becomes negative 5 over x times x, which is x squared. And this is the derivative of y with respect to x. Now, as we've already discussed, we know the slope of the tangent line is given by the derivative. At a specific x value of a, this notation is read the slope of the tangent evaluated at x equals a is equal to f prime at a. So f prime at a is a specific single value of the derivative at the point x equals a. Now, a quick algebra review for equations of lines. We know point slope form is y minus y1 equals m times x minus x1, where the point is given by x1, y1, and the slope is given by m. We also have slope-intercept form of y equals mx plus b, where the y-intercept is the point 0b, and of course the slope is m. Now let's see how we will use these concepts. In this example, find the equation of the line that is tangent to f of x equals x cubed minus 2x at the point 2, 4. Put your final answer in slope-intercept form. Now, to get the equation of a line, we need two things, a point and a slope. We already have the point, and we know that the slope of the tangent is going to come from the derivative. And to find the derivative, we have to use the definition of derivative, which is limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x. So this is going to be the limit as delta x goes to 0. F of x plus delta x means we have to plug in x plus delta x everywhere we see an x in the function. So that's going to be x plus delta x cubed minus 2 times x plus delta x. Then we have to bring down that minus sign, and then we have to put f of x, which is x cubed minus 2x, over delta x. Now, something I want to caution you about is to make sure that you put the parentheses around the entire f of x that you are subtracting. It's a common error that students make when they forget these parentheses. So this is going to equal limit as delta x goes to 0. Now, to expand out this x plus delta x cubed, we can make use of Pascal's triangle. So we know that this would be a plus b to the 0, a plus b to the 1, a plus b squared, then a plus b cubed. We will be using this row. And this, of course, gives us the coefficients of each term. So when we expand this out, the coefficient of the first term is 1. So we will have x cubed plus the coefficient of the second term is 3. So 3x squared delta x plus the coefficient of the third term is also 3. So 3x delta x squared plus the coefficient of the fourth term is 1, so that will be delta x cubed. Then we have to distribute this negative 2 to both terms here, so we get a minus 2x and a minus 2 delta x. Distributing the negative sign here, we have minus x cubed and plus 2x. Get the big fraction bar in there, and delta x in the denominator. So let's simplify. This will equal the limit as delta x goes to 0. Now let's look for everything that's going to cancel. We have an x cubed here, which will cancel with a minus x cubed there. We have a minus 2x, which will cancel with the plus 2x. And then notice that all the terms that are left have a delta x in it. So let's go ahead and factor out a delta x. Then from this first term, we will have 3x squared plus, from the second term, we will have 3x delta x plus, from here, we will have a delta x squared, and finally, from here, minus 2. Close the parentheses. In the denominator, we have delta x. This will equal the limit as delta x goes to 0. So now, of course, this delta x in the numerator and this delta x in the denominator are going to cancel. And we have 3x squared plus 3x delta x plus delta x squared minus 2. Now we can go ahead and plug in delta x going to 0. So that's going to go in here and here. We no longer have to write the limit as delta x goes to 0 because we're performing the limit. And what we will have left is 3x squared minus 2. So this expression gives us the slope of the tangent everywhere. And of course, that is f prime of x. Now that we know how to find the slope of the tangent everywhere, we can use that to find the slope of the tangent evaluated at the one specific point that we care about, which is the point 2, 4. So that means we have to evaluate the derivative at x equals 2. And when we do that, we plug 2 in for x. We have 3 times 2 squared minus 2, which is equal to 4 times 3, which is 12, minus 2 is 10. So now we know that our slope is equal to 10. Our point is equal to 2, 4. And we can plug into point slope form. Which we know is y minus y1 is equal to m times x minus x1. When we do that, we get y minus 4 is equal to 10 times x minus 2. Now the instructions said we had to write this final answer in slope-intercept form. So we need to get the y by itself. So we have y minus 4 is 10x minus 20. Then we add 4 to both sides, and we have y is equal to 10x minus 16. And this is the slope-intercept form. So this is the equation of the line that is tangent to f of x equals x cubed minus 2x at the point 2, 4. There is an alternate form of the derivative used to evaluate the derivative at a single point, c f of c. So if we know the exact point that we want to evaluate the derivative, we can use this alternate form, which is f prime of c equals the limit as x approaches c of f of x minus f of c over the quantity x minus c. Now, if we look at this diagram, the point cf of c is the known point that we want to find the derivative at. X is going to be a variable that's moving. So then the point x f of x is going to move closer and closer to cf of c as x approaches c. And this secant line will approach becoming the tangent line as x approaches c. These 2 points will get closer and closer together until they become the same point, and then the secant line turns into the tangent line, and we know that the slope of the tangent line gives us the derivative. In this example, Given f of x equals x squared plus x minus 2 at the point P, which is 2, 4, find the slope of the tangent line at P. So we have to find the slope of the tangent evaluated at the point 2, 4, which means we have to find f prime of 2. Now, because we are at a specific x value, we are allowed to use the alternate form. We don't have to, but we are allowed to use it. And sometimes it's a little bit quicker and easier than using definition of derivative. And remember, the alternate form says that f prime at a specific location of C is equal to the limit as x approaches C of f of x minus f of C over x minus C. So then for our example, we will have to do the limit as x approaches 2 of f of x minus f of 2 over x minus 2. So then that is equal to the limit as x approaches 2, f of x is given to us x squared plus x minus 2. Then we have this subtraction sign. Then we have to subtract f of 2. Now, we can either plug 2 into the function and figure it out, or we already know that f of 2 is equal to 4. Either way, we'll get 4. And we have to put that over x minus 2. Then this is equal to the limit as x approaches 2 of x squared plus x minus 6 over x minus 2. And this is equal to the limit as x approaches 2. If we factor this numerator, we see it will be x plus 3 times x minus 2, and that has to go over x minus 2. Then this becomes the limit as x approaches 2 of the quantity x plus 3, because of course in the limit we can cancel out those common factors. We go ahead and evaluate the limit, and we find out that the slope is going to equal 5. So now we know the slope of the tangent at the point 2, 4 is equal to 5. Now in part B, we have to give the equation of the tangent line and put the answer in slope-intercept form. We know that to find the equation of a line, we need a point and a slope. We know that our point is 2, 4, and our slope is equal to 5. So we can start off in point-slope form, which is y minus y1 is equal to m times x minus x1. And we would have y minus 4 is equal to 5 times x minus 2. Simplifying, we get y minus 4 is equal to 5x minus 10. Adding 4 to both sides, we get that y is equal to 5x minus 6. And this is the equation of the line in slope-intercept form. Next, we have to plot the graph of f and the tangent line. Remember that f of x was equal to x squared plus x minus 2. Because this is a quadratic, we know the shape will be a parabola, and since the leading coefficient is positive, the parabola will open upwards. Now we can find the roots by factoring. This would be x plus 2 times x minus 1, which means the roots of f are at -2, 0, and 1, 0. So we know those 2 points are on the graph. Now all we need to plot the rest of the parabola would be to know where the vertex is. And we know that the x-coordinate of the vertex can come from -b over 2a. So that's going to be -1 over 2 times a, which is also 1. So the vertex is at -1/2, and we can get the y value by simply plugging into the function. So we have -1/2 squared plus -1/2 minus 2. This would equal 1/4 minus 1/2, but let's get a common denominator and call it 2/4, minus 2, but again, we get the common denominator and call it 8/4. So that means the y value is going to be 1 minus 2, which is -1, minus 8, -9/4. So now we know the y-coordinate of the vertex is at -2 1/4. So our vertex is going to be at -1/2, -2 1/4. So if we come to our graph, over to -1/2, down to 2 1/4, here's the vertex. We also know that it's going to go through the point 2, 4. For example, if we plug in a 2, we get 4 plus 2 is 6, minus 2 is 4. So we know it's got that point. We can draw this graph. We know that the tangent line has the equation y is equal to 5x minus 6. We know it's going to go through the point 2, 4, because that's where we found the tangent line slope was at x equals 2. And we also know the y-intercept will be -6. So now we can draw in this line. And now we have the graph of f of x and the graph of the tangent line on the same coordinate plane. Next, we look at the relationship between differentiability and continuity. If f of x is differentiable at x equals c, that implies that f of x is continuous at x equals c. So differentiability implies continuity. Similarly, if f is not continuous at x equals c, that implies that f is not differentiable at x equals c. So if a function is not continuous at a particular x value, we can automatically conclude that it will not be differentiable there. If f prime of c does not exist, then that tells us that f is not differentiable at x equals c. For f to be differentiable, the derivative would have to exist. So if the derivative doesn't exist, that means f is not differentiable there. A sharp turn in the graph at x equals c implies that f of x is not differentiable at x equals c. So we could conclude that f prime of c does not exist there. Finally, a break or a jump in the graph at x equals c implies that f of x is not differentiable at x equals c. Again, that means the derivative does not exist there. So if we have a sharp turn or a break or a jump in the graph at x equals c, that tells us that f prime of c does not exist. In this example, discuss the differentiability of f of x equals the cube root of the quantity x minus 1 at x equals 1. To discuss the differentiability, that tells us we need to find the derivative. And since we are at a specific point, we can use the alternate form of the derivative, which is often the simpler form. Now remember that f prime of c is equal to the limit as x goes to c of f of x minus f of c over x minus c. And when we can use this alternate form, we like to, because often it's a little bit simpler than using the definition of derivative. So then in our case, f prime at x equals 1 is going to be the limit as x goes to 1 of f of x minus f of 1 over x minus 1. So that's going to be the limit as x goes to 1 of the cube root of x minus 1 minus f of 1. If we plug in 1, we get 0 over x minus 1. Now this is going to simplify to be the limit as x approaches 1. Now here we have like terms. Let me write it in a simpler way. The cube root of x minus 1 is just x minus 1 to the 1/3 power, and then in the denominator we have x minus 1 to the 1st power. So then that means this is going to be 1 over x minus 1 to the 1 minus 1/3. So that's going to be 1 over x minus 1 to the 2/3. So that's what we put right here, 1 over x minus 1 to the 2/3 power. Now we can do a direct substitution, and this turns into 1 divided by 0, which of course is undefined. So what we just found is that f prime of 1 does not exist. Therefore, f is not differentiable at x equals 1. In this example, determine the x values where the function exists, is continuous, and is differentiable. Here we have a graph of f of x. When we determine where f exists, that means we are looking for the x values that we are allowed to plug into the function, and it will result in a y value. And since there are no x values that we are not allowed to plug in, that means f exists everywhere from negative infinity to positive infinity. To determine where f is continuous, since we have the graph, we see that we can draw it on its entire existence without ever having to pick up our pencil. There are no holes, asymptotes, breaks, etc. So in this case, f is also continuous everywhere. So from negative infinity to positive infinity. To determine where f is differentiable, we have to decide at what x values does the derivative exist. And we've learned that anywhere that there's a sharp turn in the graph, the derivative doesn't exist there. So because there's a sharp turn here at x equals -1, we have to say that f prime of -1 does not exist. And that means that f is not differentiable at x equals -1. So then to say where f is differentiable, we would say from negative infinity to -1 union -1 to positive infinity. Here we have the graph of g of x. So pause the video, try this one on your own, then restart when you're ready to check your answers. Now g exists everywhere that we can plug in an x value and it will result in a y value. And that happens everywhere on this graph except right here at this vertical asymptote, which is at x equals -3. So then g exists from negative infinity up to -3 union -3 to infinity. Now g is continuous everywhere that we can draw the graph without ever having to pick up our pencil. And that's going to happen as long as there's not an asymptote or a hole or a jump or a break. Now, because of this vertical asymptote at x equals -3, we know that g is not continuous there. And because of this hole here with the jump up to that point, we know that g is also not continuous at x equals 1. So then we can say g is continuous from negative infinity to -3 union -3 to 1 union 1 to infinity. To determine where g is differentiable, we have to look at the places in the graph where there are jumps, breaks, sharp turns, holes, asymptotes, all those things where the derivative would not exist cause g to be not differentiable there. So that happens here at x equals -3. It also happens here at x equals 1. So then g is differentiable from -infinity to -3 union -3 to 1 union 1 to infinity. Now you will learn about one-sided derivatives. The derivative from the left uses this notation, and you would say f prime from the left at c, or you could say f prime of c from the left is equal to the limit as x approaches c from the left of f of x minus f of c over x minus c. Similarly, the derivative from the right, and you could say this f prime of c from the right, or you can say f prime from the right of c is equal to the limit as x approaches c from the right of f of x minus f of c over x minus c. So both of these are using the alternate form of the derivative. Now for f to be differentiable at c, we need the derivative from the left at c to equal the derivative from the right at c. In this example, given f of x equals absolute value of x minus 4, determine if f of x is differentiable at x equals 4. Now, because f is the absolute value function, we've learned that we need to first write f as a piecewise function. So f of x is going to equal the opposite of x minus 4 if x minus 4 is negative, which happens when x is less than 4, or it will be x minus 4 if x minus 4 is greater than or equal to 0, which is when x is greater than or equal to 4. We can put this on a number line. The changeover happens at 4. When we approach 4 from the left, we are using this piece of the function, negative x minus 4. And when we are approaching 4 from the right, we are using this piece of the function, x minus 4. Now, before we can decide if f is differentiable, we first have to know whether f is continuous or not. Because remember, one of the rules we learned is that if f is not continuous, then f is automatically not differentiable. So first, we will verify that f is continuous at 4 by walking through the 3 steps of the definition of continuity. Step 1 says we have to look at f of 4. And f of 4 exists. We plug it into this bottom piece and get 0. So far, so good. Step 2 says we need the limit as x approaches 4 of f of x to exist. Now, because we have a piecewise defined function, we can't do a two-sided limit directly, so we need to do the one-sided limits. The limit as x approaches 4 from the left When we're coming into 4 from the left, it means we're using this piece, which is the opposite of x minus 4. And if we plug 4 in, we get 0. So that one exists. Then we have to look at the limit as x approaches 4 from the right. When we're coming in from the right, we have to use this piece, which is x minus 4. We can do a direct substitution, and that also equals 0. Now, because the limit from the left is equal to the limit from the right, therefore, the two-sided limit as x approaches 4 of f of x is equal to 0. So then it exists. Now, step 3 is that the limit has to equal the function value, which it does. The limit as x approaches 4 of f of x is equal to f of 4. So f is continuous at x equals 4. So far, so good. Because if this had turned out to be not continuous, we would immediately say, therefore, not differentiable. Now, we just learned that for f to be differentiable at c, we need the derivative from the left to equal the derivative from the right. So let's go ahead and compute f prime at 4 from the left and f prime at 4 from the right. F prime from the left at 4 will be the limit as x approaches 4 from the left of f of x minus f of 4 over x minus 4. And this will equal the limit as x approaches 4 from the left. When we're coming into 4 from the left, f of x is this definition, negative x minus 4. And then we have to subtract f of 4, which we know is 0. Put all of that over x minus 4. And we can see that the x minus 4 in the numerator will cancel with the x minus 4 in the denominator, and what we have left is negative 1. So that is the derivative from the left at 4. Now let's do the derivative from the right at 4. And that will be the limit as x approaches 4 from the right of f of x minus f of 4 over x minus 4. So this will be the limit as x approaches 4 from the right. When we're coming into 4 from the right, f of x is going to be this piece, x minus 4. We have to subtract f of 4, which we know is 0, and we have to put that over x minus 4. Now the x minus 4 in the top will cancel with the x minus 4 in the bottom, and this is equal to 1. So now we have to decide if f is differentiable at 4 and explain. Now what we discovered here was that the derivative from the left at 4 was not equal to the derivative from the right at 4. Therefore, f is not differentiable at x equals 4. Another way of saying this is we could say that f prime of 4 does not exist. So when the derivative from the left of 4 and the derivative from the right of 4 were different values, we can say that the derivative at x equals 4 does not exist, and that means f is not differentiable at x equals 4. In this example, given f of x equals the piecewise function 8 minus 2x squared when x is less than 1, and 7 minus 4x when x is greater than or equal to 1, determine if f of x is differentiable at x equals 1. Let's get the number line. The changeover happens at x equals 1. And when we are coming into 1 from the left, we are using this upper function, 8 minus 2x squared. When we are coming into 1 from the right, we use this lower function, 7 minus 4x. Now remember, for f to be differentiable at x equals 1, we first have to know if it's continuous at x equals 1. So let's walk through the 3 steps in the definition of continuity. First, we have to decide if f of 1 exists. And since we can plug 1 into the function, we would get 7 minus 4 times 1, which is 3. So far, so good. We've passed step 1. Step 2 says we have to do the two-sided limit as x approaches 1 of f of x and find out if it exists. Now, because we have a piecewise defined function, we can't do a two-sided limit directly, so we need to look at the one-sided limits. So if we do the limit as x approaches 1 from the left, that means we have to use this 8 minus 2x squared piece. And doing a direct substitution, that's equal to 6. The limit as x approaches 1 from the right means that we have to use this 7 minus 4x piece. And if we do a direct substitution in there, this is equal to 3. Now, because the limit from the left and the limit from the right are two different values, we have to say that the limit as x approaches 1, which is the two-sided limit of f of x, does not exist. Now, since the limit as x approaches 1 of f of x does not exist, we know f is not continuous at x equals 1. Therefore, f is also not differentiable at x equals 1. Remember, we have that rule that says if f is not continuous at c, then f is not differentiable at c. When we were walking through the 3 steps of the definition of continuity, The limit did not exist, which says that f is not continuous at x equals 1. Therefore, we can immediately conclude that f is not differentiable at x equals 1. Now you will learn about drawing tangent lines on a graph and analyzing slopes. In this example, given y equals f of x in the figure, draw in the tangent line at each point. So pause the video to try this one on your own, then restart when you're ready to check your answers. At point A, the tangent line would look approximately like this. At B, like this. At C, about like that. At D, and at E. At which points is the slope of the curve negative? We can see that the slope at A is negative. The slope at C is negative. At which points is the slope of the curve positive? This is a positive slope here at B. There's a positive slope at D and a positive slope at E. Using A through E, list the slopes in decreasing order. So the steepest slope out of A, B, C, D, and E is here at point E. The next steepest slope appears to be here at point D. Then at point B, it's still positive, but the slope is getting smaller. Next would be A, because it's negative, but it's not as negative as C is. So C is a larger magnitude negative, so that would actually be the least of the slopes. In this example, given the graph of f of x, sketch a possible graph of f prime of x. So here we have a graph of f of x, and from that graph, we can build a graph of f prime of x. Now remember that f prime of x just comes from the slope of the tangent lines. Sometimes we just say from the slope of the graph. And particularly in this case, since the graph is just line segments, so the derivative is going to come from the slope. Then what we do to build f prime is get the slope of f of x, and that gives the y values of f prime of x. And that's what this statement means. The slope of the function gives the value of the derivative. So let's take a look at what this means. From negative infinity all the way up until negative 2, we can calculate the slope here. We see it goes up 1 over 1, up 1 over 1. So pretty easy to see that the slope of this section of the graph is 1. So from negative infinity all the way to negative 2, we know the slope is 1. That slope of f gives us the y value of f prime. So that means when we come down here to the graph of f prime from negative infinity all the way until negative 2, we know the y value will have to be 1. And now right at negative 2, we put an open circle because that's the point where it's changing over from one piece to a different piece. So because the slope of f equals 1, then the y value of f prime equals 1. Now, if we look from x equals negative 2 until x equals positive 2, the slope of this part of the graph is 0. Then that means from x equals negative 2 until x equals positive 2 on the graph of f prime, the y value has to be 0. So we have an open circle here where it changes over, and an open circle here where it changes over. And then in between there, the y values are all 0. So once again, the slope of f of x gives the y values of f prime. Since the slope of f is 0 from negative 2 to 2, that means the y values of f prime have to be 0 from negative 2 to 2. Now from x equals 2 to x equals infinity, we can find the slope of this part of f. Looks like we go down 1, 2, 3, and over 1. So we can label this, the slope is negative 3. And once again, the slope of f of x gives the y values of f prime. So then that means from x equals 2 on to x equals infinity, the y value of f prime is going to be negative 3. We put an open circle right at x equals 2 where it changes over. And we put y equals negative 3 there. So from the slopes of f of x, we got the y values of f prime. From negative infinity until negative 2, the slope was 1. That's why the y value here was 1. From negative 2 to positive 2, the slope of f was 0. That's why the y values of f prime were 0. And then from 2 to infinity, the slope of f is negative 3, which means the y values of f prime have to be negative 3. Now the slopes of f were pretty easy to find in this case because of the linear pieces going on. Typically, we're going to be dealing with curves, and so rather than getting an exact slope, we're going to have to estimate the slopes. So let's see how that works. So now you'll get some practice at estimating slopes on a curve. In this example, estimate the slopes at the given points. What I want you to do is pause the video and estimate the slopes at these first 3 points. Then restart the video to check those. Then pause the video again and do the next 3 or 4 points. Restart the video to check those, and then pause it again to try the next ones, and then restart to check. So go ahead and find the slopes at these first 3 points. To help you understand how we will estimate the slopes of tangent lines, let's take a look at this graph. We can put a point on the graph and draw the tangent line in there. Now, if we had to estimate the slope of this line, we could say maybe from the point, it looks like we're going down by 5 and to the right by 1. So that would be a slope of -5. And again, we're just estimating. Somebody else might have said it was -3 or -4. All those answers would be fine. But say we said this was a slope of -5. Now we let the point move along. And you can see here, for example, the slope is still negative, but now if we start at the point, maybe it looks like we're going down 2 and over 1. So if we estimated that slope up here at -5, maybe we would estimate this slope at -2. And if we continued on, here it looks about like a 45-degree line. So from the point, maybe it looks like we're going down 1 and over 1. So we would estimate that slope at -1. If we continue to move the point, now maybe it looks like from the point you go down 1 and over by 2. So that would be a slope of -0.5. And you can see that the slope gets smaller and smaller magnitude, staying negative until right here, when the slope is actually 0 because the tangent line is horizontal. Now, if we let the point move again, maybe it looks like from the point we go up 1 and over, say, 3. That would be a positive slope of 1/3. Maybe if we're here, looks like about a 45-degree angle there. From the point, looks like we go up 1, over 1, so maybe that's a slope of +1. And you can see as the point moves along the curve, the slope is getting steeper and steeper, which means the number we use to estimate it should be getting bigger. So this might be estimated at 2 because we go up 2 and over 1. And if the point continues to move, maybe that's about a slope of 3, and that's a slope of 4, and that's a slope of 5. All you're doing is estimating the slopes compared to what you've already kind of estimated as you're going along. In this example, given the graph of f of x, sketch a possible graph of f prime of x. Now remember, we've learned that the slopes of f become the y values of f prime. Now on this graph of f, there are 2 locations where we know exactly what the value of the slope is. Here at -1, we know the slope of the tangent line is 0. So that tells us that f prime of -1 has to equal 0. So that means the y value of f prime at x equals 1 is 0. So because this slope right here is 0, we come down on the graph of f prime and we have to put a y value of 0. The same thing happens at x equals 1. Right here, we see that the slope of the tangent is 0. So that means f prime of 1 is exactly equal to 0. So we come down here and put a y value of 0. Remember, the slope of f gives the y value of f prime. Now what we want to do is estimate the slope at a few points on the graph. So for example, if we estimated the slope here, drew in the tangent line, maybe we guess that that's about a slope of 3. It looks like maybe we're going up 3 over 1. If you said 2, that's fine. But we come down here and we say, well, maybe that's about 3. Then maybe we would choose to pick a point about here. If we draw the tangent line there, maybe that slope kind of looks like we're going up 1 and over 1, so maybe that's a slope of 1. So we would come down here, that slope is 1. And now this makes sense because as we go along, the slope is steeper here, it's less steep here, it's getting smaller and smaller and smaller and smaller as it comes in to 0. So the slope is bigger, then getting smaller and smaller and smaller as it comes in to 0. Now from x equals -1 all the way until x equals +1, we see that all the slopes along this portion are going to be negative. So for example, maybe if we picked this point, drew in the tangent line, maybe we would estimate that as down 1 over 1. Maybe that looks like about a slope of -1. So we would put, maybe that slope is -1. Now right here at x equals 0, the tangent line looks like it's going to be the steepest negative value, because after this it's still negative, but it's getting closer and closer to 0. So if we called this -1, I suppose we'd call this -2, or we could call it -3. There's lots of choices. Since the slope here is the steepest negative slope, and after that it starts going back up to 0, we know that that will be the lowest y value on the graph, the most negative, if you want to think of it that way. So if we kind of connect these dots here, now after x equals 0, the slope is still negative, but you can see it's heading up to 0. So that means the y values will still be negative, but they have to head up to 0. And that makes sense with connecting to this point here. Now after x equals 1, so for example, let's just put a point here, the tangent line there, we can see it's positive. So here we know it's 0, and then it's slightly positive, more positive, more positive, more positive. So maybe this slope is approximately 1. So we know that means on the graph of f prime, the y value would have to be 1. And then after that, the slope just keeps getting steeper and steeper, meaning more positive. So goes up that way. So from our graph of f, we estimate some slopes on there. We knew the exact value that the slope had to be 0 here and 0 here, so that helped us anchor a couple of points there. And then we look at the trends. The slope started out as a steep positive, so the y value starts out as a large positive. The slope is positive but getting smaller going to 0, so the y values are positive but getting smaller going to 0. Then from -1 to 1, all the slopes are negative, so it's a small negative. It gets the steepest right there, so the y values, small negative, gets the most negative here at x equals 0. Then the slopes are still negative, but going up to 0, so negative, but going up to 0. Then the slopes are getting bigger and bigger and bigger, which means the y values get bigger and bigger and bigger on f prime. It's time to check your understanding, so pause the video, try this one on your own, then restart when you're ready to check your answer. So the slope all along this curve is negative everywhere. let's just put a few points in, draw the tangent line there. We can see that this is a pretty steep negative slope. Maybe it looks like we're going down 3 and over 1. So I'm going to call that -3. Maybe you called it -4. Doesn't really matter. It's all relative. But if I call this a slope of -3, then I'll put that y value here on the graph of f prime. So since this is the steepest slope on the graph in the negative direction, that means this will be the farthest negative point on the graph of f prime. Now maybe I'll look at a point around here, put in the tangent line, and that slope is still negative, but it's going to be a smaller magnitude number. So if this slope was -3, maybe this slope is -1, or maybe you said it was -2. So we come down here and put a y value of -1 on the graph of f prime. Now I'll come along, let's put a point here, get the tangent line. Now this is a very shallow negative slope. Looks like maybe we go down 1 and over 2, so maybe this is a slope of -0.5. And you can see if we continue along the curve, the slope is going to get closer and closer to 0, but always be negative. So then that means our graph of f prime is going to look something like this. So once again, it started out the steepest negative slope, so that should have been your most negative y value on the graph of f prime. Then, as you go along the curve, the slope is still negative, but it's getting closer to 0 as you go along. So all the y values are still negative, but getting closer to 0 as we go along. And now here, I've just made a quick summary of derivative formulas that you learned in this lesson. Definition of derivative gives the formula for the derivative at every x value, and that's f prime of x is equal to the limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x. And this will give you a formula that you can then plug in x values to find the derivative. The alternate form finds the value of the derivative at one specific point, x equals c. And that is f prime of c equals the limit as x approaches c of f of x minus f of c over x minus c. We also learned about one-sided derivatives. We use those a lot, particularly with piecewise defined functions. It finds the value of the derivative at one specific point, x equals c, coming in from only one direction at a time, either left or right. So this notation means f prime of c from the left, and that would be the limit as x approaches c from the left of f of x minus f of c over x minus c. Whereas this notation means f prime of c coming from the right, so we do the limit as x approaches c from the right of f of x minus f of c over x minus c. So these one-sided derivatives use the alternate form, and both of these, meaning the alternate form and the one-sided derivatives, are evaluating the derivative at one specific point, x equals c. Whereas the definition of derivative gives the formula that would allow you to find the derivative anywhere.